Hey, all. As soon as you hit stream, people are hearing dead air. I know you're waiting for the tunes that I can't hear, but...
That's okay. Hello, everybody. I don't know who's actually, whether we're even streaming now. As soon as I hit start stream, I don't know how long it takes for the stream to actually begin. But I just wait a little bit.
MMT beat me.
Oh, MMT. Hey, what's going on?
Oh, hello, Cypher. Hi, Tana.
Cypher2 Productions is here.
Yeah.
Cypher2 Productions is in the house.
Stream just started, so...
Nice. I did announce that we were going to be here, so I understand.
Did you announce it in our group as well, or just on your page?
You know what? I think the one group I didn't put it in was SkyTour LiveStream. I put it in every other group, including FX Models, Planetary Replicas. Can you? Are you able to do that?
Yeah, I'm posting it on my wall first.
Thank you. Tana's here. Hey, Tana, what's up? Andy's here too, huh?
Hi, Bon Bon.
Bon Bon?
Bon Bon.
Bon
He
Bon?
calls me Foxy, so I call him Bon Bon.
Oh, okay. And who's Bon Bon?
Bon Bon. Bonnie from Five Nights at Freddy's.
Oh. Okay.
Well, that's where Foxy came from. You probably don't remember.
I don't.
Well,
no, wait,
Foxy.
Foxy.
I sounded like a pirate, and I said if I have to be a pirate, could I at least be Foxy the pirate?
Is that something from an anime thing or something?
Video game.
A video game. Okay, gotcha.
Five Nights at Freddy's.
Gotcha.
One day maybe I'll play.
Wow.
I can't bring astronomy to you guys. I don't have a telescope, so.
Ooh.
And I'm not a gamer either, but it's a horror game.
That's
and
a
there's
bad
lots of
thing.
jump scares, so you might have a good
That's
laugh.
a bad thing. Well, that's okay. That's okay. Well, hey, listen. Welcome to the stream once again. This is Mark D'Antonio, as you know. And I want to just make it clear to you guys that this is a third stream this week, which is wonderful. And I'm going to try and do more streams for less time. And that's kind of what we want to do. Hi, Dee. How you doing?
I was just about to say, Dee in the house.
I saw. Yeah, I'm actually got the chat up while I'm away from the scope at the moment. So I will be putting this behind me in a second here. So I won't be able to see it in a minute.
I'll still be taking
and you
questions from chat. I'll keep my eye on chat.
Fantastic. And tonight what we're going to do is we start on the moon because the moon's out, but I also want to take us to some nice double stars, which we're going to do in a little while. I just want to make sure that my sound levels are good. I changed the sound level on the music a little bit, and I want to just make sure that I don't keep that too high. And I think that this may be okay, but you guys tell me what you think. I have the sound level at this setting. How does my voice sound right here? If this sounds good, we will continue from here. I'll just wait the allotted amount of seconds before I move on. But,
and for some reason, I think that kind of tinny echo might be back on my voice. I'm not sure. You can let me know, but I don't know what we can do about it.
Yes, Danny is inside. Amanda's inside of a tin can. Doing the show tonight because she's not in the house. They banished her from the house, and now she has to live inside of a tin can in the backyard.
Maybe I made my own dome.
Or maybe she made her own. Actually, you sound like you're in a dome. That's actually correct. Because when I had the central mic in here, when I was doing this originally, when I started, I had that echoey sound. I think you're trying to become a streamer. Oh, wow, that's impressive. But
no, well, I don't know what it could be. I haven't changed anything that I can think of.
No worries. But so tonight we're going to look at the moon for a little bit, and I just thought this was a pretty interesting location on the moon because there's an interesting set of craters right here that we can look at that are really cool, and that's interesting. I'm actually getting motion. That means that my pier is no longer movement isolated from the rest of the dome. That's a new thing. I will have to change that. I will go back. Now I'm touching the telescope, so it's okay. Oh, I see what it is. Okay, now I'm going to just bring this down a little bit and then come back in. So as I do, then we'll see a little bit differently here. All right, now if I move us over just a bit, go check out some other things. Oh, I just love that. Look at that. Right in the center, you see there's a straight rill that you can see. It just goes really straight. These are obviously they're either impact related or volcano related, and so we're actually looking at a very what we call a very varied terrain on the moon that is the result of either volcanism or impact. Obviously, there weren't really a whole lot of earthquakes on that is moonquakes on the moon. There were no earthquakes on the moon, but if you notice, I always like to look at the shadows of things, and using those shadows, we can do all kinds of crazy things like calculate the heights of the mountains and so forth, depending on the sun angle. If you know the elevation angle, and you can measure the length of the shadow accurately, you can actually calculate the height of the mountains on the moon. I'm not going to go through that with you right now, obviously, but we will do that, and maybe we'll save that for an indoor, lunar reconnaissance orbiter stream, which would really be a lot of fun. I know that people will like that because I will teach you how to use the new Lunar Reconnaissance Orbiter Quick Browser. And this time I will name the stream appropriately so that we won't get banned for another 90 days. So that made me crazy. Anyway, can you tell?
Someone actually heard that story for the first time the other night.
Really?
Yeah. I
Wow.
thought everyone knew why.
That's all right. I mean, why would they know?
You mentioned it several times.
Yeah, why would they know? I know, but they wouldn't necessarily know or expect to know. I mean, I'm okay with that. They're good people. They forgive me for things that happen sometimes.
We hope.
I think they will.
I think they will too.
Yeah, I didn't actually send that out. That video that went up that I didn't know about. Was only 11 seconds long, and that was the killer. 11 seconds long with no content and no video, and it got me banned from YouTube for 90 days. Oh man, I was so angry at YouTube because there's no one you can talk to. No one, absolutely no one. Ta-da!
But
you're
at
done.
least it was during the cold months.
That actually was a saving grace. You're right. So I mean, if you have to say there's a good thing about it, okay, well that's a good thing, But I have to tell you that I'm really, really glad that we didn't have to go through this anymore. I'm pleased that it's like it is. It's okay. I have it back. That's all that matters. And I want to take us off the moon, guys. I know that we're having so much fun on the moon, but I'm going to take us away from the moon, if you don't mind. I'll just give us an overall view of the moon first, because it's 57% full. This is waxing gibbous moon, and it's really, really pretty, obviously. And on P&K yesterday, an object crossed the moon that was moving fairly slow. And if I had to guess, it probably took more than 20 to 22 seconds to cross the face of the moon. And usually what I do is I calculate exactly where it is, if it's a satellite and so forth. But this one actually had a distinct shape. Now, at that distance, that it had to be moving so slowly, because the farther away something is from the planet Earth that's in orbit, the slower it's going to move. But at that distance, this object that had a very definitive shape would have had to literally have been moving or been massive in size, And so the theories can begin. People can say, hey, there's a big massive thing moving on the moon or whatever, or near the moon. Or maybe it wasn't out in space at all. It's possible that we were actually looking at something in our atmosphere, like a weather balloon. Now, that's something else that happens that we don't really think about, but we get weather balloons all the time being released. And it had the shape that looked like what you might expect to see if you were looking up at a weather balloon going overhead, very high. And it was traveling from west to east. So that would make sense down in Miami, where Paul was actually doing this. And it's possible that we were looking at a weather balloon, but we won't know unless we can actually get an indication. This is gorgeous. Now, the other thing I wanted to tell you is for tonight, because we're going to be looking at double stars and we want to see their color, I removed the special filter that I've had on the telescope for months. All right, and that took a little work, but I wanted to take this filter out so that we could see it in more of a true color. The filters allow us to see things really, really, really more detailed wise, and allow us to take shorter exposures to get detail, whereas usually we have to take long exposures to get detail. But with this camera, we get this beautiful scenery without having to wait a long time. I'm just playing with the telescope here for a second. So, that said, we'll come back to the moon perhaps a little bit later. It really does look nice. I'm having trouble wanting to leave it, actually. But I'm going to take a quick photo of the moon. Yeah, that's not the moon. I'm actually I'm going to move us down to a delay for the photography. Here we go. Okay, 2-second delay, and then the picture's taken. You might hear that little click in the background. That's not even a real click. It's an artificial click to make you think something happened. Otherwise, you don't know. With a digital camera, it doesn't make a solid click. There's no shutter in this particular camera. It's shutterless and mirrorless. The shutter's electronic, so the chip is always exposed to the light, and only when they want to take a picture do they actually activate the chip. Now, we do have clouds moving in, so we're going to move quickly here to try and get a hold of a few objects. The clouds are supposed to come in around midnight, so we have technically, we have a couple hours here before that happens. So let's go to our observing list and let's try to get to the first object up for bids here on The Price is Right. All right. Now, I told you we're going to be going to some objects like double stars, and that's exactly what we're going to do. So let's go there.
I was waiting for you to say, but first, we're going to look at this.
I know, right? I do that, don't I?
Sometimes.
Oh, here we go.
Let's keep people on their toes.
Yeah.
Oh, wait. Jenny's in the house.
Oh, you didn't want to.
So.
That's funny. That's great. All right, let's see if we can. Let me now make this camera able to see what we're trying to look at here. We're going to go to just 10,000. We don't even need to go very much. We're here to look at a double star that's pretty interesting. And let's see.
Tana has a question, and I think we kind of talked about this on our last stream.
Okay.
I think it was the last stream.
All right.
She wants to know why is that we can't see the stars behind the moon. That's because you're trying to get rid of the stars so we have more detail to see the moon, right? That's like.
Oh yeah. I mean,
filters you're using. Or?
Yes, exactly right. And now we know, because at first I was going to say, well, because the moon's solid and we can't see through it. And the way you asked the question, and then I was like, wait a minute, that must be the way you're asking the question. And I kind of snickered to myself because I knew that wouldn't be the case. That was, we can't see the stars around the moon because of the fact that we're shooting an exposure for the moon. And if we overexpose the moon, then we will see the stars. That's exactly why the Apollo hoaxers are wrong. They're totally wrong all the time with this, and they don't get it. They just continue to pursue this as if they know what they're talking about. You set the settings so you can take a picture of the moon, and you set the settings so that you actually get sorry, I'm just changing the music volume here because it's too loud for me. Never mind you guys. I have it turned down for you. All right, so we'll turn it down a little more. There we go. Now you probably can't even hear it. All right. Anyway, yeah, and I haven't even focused yet, so I have to still focus everything we're looking at here. So. Yeah, so you have to set the settings to be appropriate, and if you don't, then you're not going to be able to see the moon clearly and with the right exposure. It's going to be overexposed and blown out, and we don't want that. We don't want that at all.
And you were kind of using Jupiter and its Galilean moons as an example.
Yeah, but I could actually use the moon if it had a bright star around it last night, but it didn't. Yeah. So I was thinking of trying to use that, but. Anyway, that's okay. So this is our first double star of the evening. And the thing is, you can't actually even see that this is a double star. And I started with this star because you can't see it. And you might say, well, what are you doing? Well, I'm trying to point out that there's stars that look like one star that aren't. Now you see a star above this. That's not actually in this system. That's a field star, as we call it. Okay, this star here is actually a double star, and this is a star that's known as Alpha Coma Berenices. It's the brightest star in the constellation of Coma Berenices, which is Berenices' hair. And it's a magnitude 4 star, 4.3. And the thing is, it's actually just a little bit fainter than the star that's labeled Beta. This is Alpha. Well, Beta is actually a little brighter, but it's interesting why it's called a the Alpha star when it's not the brightest star. Usually we label them Alpha, Beta, Gamma, Delta in order of brightness. Now, what we're looking at here, you can't tell again, but the star's got a second companion, and it's only literally 0.5 arc seconds in separation between the main star. Now, to understand what that means, if you look here, the star itself, the bloated image of the star itself, is more than 1.5 to 2 arc seconds in size. It's actually more like 4 arc seconds in size. So the companion would be inside the glare of the star as seen in this telescope. But with a space telescope, we wouldn't see that. We'd see something very different. And we could probably, with proper equipment here on Earth, photograph that star. But it's literally only it's only half an arc second from the star. All right, in terms of the angular view in the sky. What's that mean? In real life, it means it's 9 astronomical units, 9.5 astronomical units from the star. Now, that's a third of the way to Neptune. And you say, wow, for it to look like one object, it must be far away. And it's 58 light years away. And it kind of gives you a feeling for how far light years really are. It's just a really interesting sight. So I know it doesn't show you much the first one, but that's okay. I think it's important to understand how some can't be seen, and they're called, some of the ones that don't show a double star are called spectroscopic binaries, and only in the spectra, which is what that means, only in the spectra do you actually see that there's a double star, that there's another star contaminating the star's spectrum. Really cool. Very, very interesting. Now, let's see, okay, there's Arcturus. So now, if we move on to another one, what I'd like to do is to take us by, this next one is called Epsilon Buddhist, and we're going to go there now. Now, Epsilon Buddhist actually is in the constellation of Bootes, the sheep herder, and it's a neat constellation, but it doesn't really have a whole lot in it. And when I was a kid, seeing Buddhists come up, I was like, oh, great, Bootes. Nothing to see here. Move along, But it's actually not true. It's actually pretty cool. And we might not even see this one, depending on the night, because it's kind of we got the moon out and so forth. But let's try it. All right, I'm going to move it over. And then we'll talk about that's the wrong way, Mark. I'm Wrong Way Feldman. Who in chat remembers a guy named Wrong Way Feldman? Let us know. All right, and let's move in here. Let's see if we can see.
It seems vaguely familiar, but I don't know. So chat, it's up to you guys.
Yep. Yeah, my little trivia. Useless trivia. Now let's try to focus and see if we can catch this. I doubt it. Let's try. I'm trying to just focus and bring this in. Yeah, ain't there. I can't see it. Yeah, this star is also not showing me the double. which I can't believe, because this is actually a pretty blatant star. You should be able to see this one. But it is only 3 arc seconds, and I guess that's asking too much for a wide field scope like mine. So I guess that makes sense. But no problem. We will go to another one, because I know there's some good ones coming up. Now this one here. This one is Alpha Canis Veneticorum. And this guy has a separation that is clear. So let's go there. And where is this one? Well, it's kind of over near...
Berenices here?
No, it's actually...
Not in, but near. We couldn't have been that far, were we?
No, it's not that far from this. Okay, but we can already see the double from this. You can already see the double star here.
I do.
Down at the bottom. And it's going to just settle up. Now, my objects, the way I have the scope aligned right now, the objects are just a little lower left of center. And trust me, that's wonderful compared to what it used to be. It's like hunt and find it. Where is it? Where is it? So now we move it over. And again, we're going to see these now in the real color they are when we actually do our color test, which you know that I like to do. So this...
when you said you switched filters, I got excited. I thought we were going to be looking at the spectrum.
Oh, I see what you mean. Yeah, well, I do have to do the spectra this way, you know, without... I do have to do the spectra without any kind of filters so that we can actually get the proper colors. Wow, that's really pretty. Now let me just try focusing a little. Now I'm going to go out of focus a little just to show you the color difference. See the difference? Look at that. We have a blue star and we have an orange star. Isn't that pretty? Now I'm going to bring those down into focus.
See, I could barely make out the orange until, like, they both looked white.
Okay.
But, like, the background of the bigger one had a kind of bluish to it. But if you said what colors are these, I probably would have said both white. And then after you said orange, it's like, okay, I see the palest little hue of orange.
Well, then let me do this. I know it's gonna go out of the view, but how about that?
Wow.
Now you can see, right?
Well, I see the 2 rings, but it's going away.
I know it's going away.
I see the two rings, but again, I still don't see the orange. Now it looks white and kind of pixelated bluey.
It does. It does. But what's interesting is the which star turned orange and which star was blue. The bottom right star was orange, and the upper left star is blue. But when we actually defocused this, we actually saw something different. We actually saw that one of the stars actually looked, the blue star actually looked orange. Okay? Alright. See that?
I see what you're doing, but...
Okay, you can't see the color.
It might just be my eyes. I mean, do you guys in chat listening? Like, I can make out the blue. I get the blue, but...
Okay.
My eyesight is not good enough to see the orange. But
right.
It's like, once you made the suggestion that was orange, I can kind of see it. But I mean, if you had to set another color, I'm wondering if...
Well, let's do this. Let me take a photograph. Alright, let me just take a picture of it. And now let me go in, and let's zoom in on it. Yeah, it doesn't help. I'd have to actually... It's
a nice picture, though. It's very, very pretty.
It is. But I would have to actually play with this to get it to look like that. To get the colors exactly right. But
maybe it's just my eye picking up too much blue because the other star is so much bigger.
Yeah, it's
so blue.
Well, it's brighter. They're actually not very much different in size.
Really?
Yeah. See, that's the thing. Brightness matters. You know.
Yeah.
So let's see here. This is the overall stars together are magnitude 2.8. All right, and you know, Vega, for instance, is 0. The Sun is -26. So you can see, you know, the brightness goes up as the numbers go smaller and then negative. And this object here, these 2 stars, they're dominated by that white A0 dwarf, which is that one to the upper left. Okay, and its surface temperature is 10,000 degrees, like A stars typically are. That's 0, OB, AF, GKM, in your favorite
OB, fine guy, kiss me.
Yep, your spectral classes there. All right, and that's actually the A0 dwarf. All right, and then we have an F0 star, which is a little more orange. Okay, what you see to the lower right there, and that's actually that F0 star, and they're actually both they're burning, I should say, fusing hydrogen into helium. They're actually fairly normal stars. As far as I know, I'd have to look at the research on those. I think these stars are actually just normal stars. I know that the A0 star is. So, excuse me. But this is a beautiful double star to start out with that I think is gorgeous. Now, as far as the distance away, okay, these stars are 115 light years away. Okay, and they're separated by 679 astronomical units. If you got to their sky, you'd actually see them separated by that far. Now that means that if at the sun, they'd be definitely out in the Oort cloud. The other one would be out in the Oort cloud if one of them was placed where the sun was. If the F0 star, the one on the right, was placed where the sun is, that other one would be out by the Oort cloud, and it would dominate. Wow. It would dominate the night sky. It'd be really bright.
I kind of get that now, guys. So, the Oort cloud. If you think of where our sun is, the Oort cloud is like way past Pluto.
That's right.
It's past Neptunian. Neptunian objects.
Listen to you.
The Kuiper belt.
That's right.
The Oort belt is past the Kuiper belt, so that.
And you didn't.
I wish I could put these pictures in chat because I had a really good one of. Okay, the asteroid belt is between Mars and Jupiter.
Yeah.
The Kuiper belt is past Neptune.
Yep.
And then the Oort cloud, again, think of it as a belt if you want, is past that.
Well, yeah, and that's that Oort cloud too. That the Oort cloud, we call it a cloud as opposed to a belt, and there's a reason. The Oort cloud is actually a belt as well, out beyond the Kuiper belt, which is a belt of icy objects past Neptune, like you just said, and that location is also it's a transition zone. We have beyond that disk of the Oort cloud, we now get to areas where the objects sort of surround the sun in a halo rather than a disk. So the Oort cloud is both a disk and a halo, a spherical halo around our sun. And that's something that is really fascinating because we didn't really know much about the Oort cloud. And then if you remember our show on KGRA, SkyTour Radio, we actually talked about other objects out there, and they're known as SDOs. Do you remember what SDO stands for, Amanda? Scattered disk object. Yeah, I was gonna make it. It's okay. I took it away from you. I wasn't gonna, wait. It was crazy. And scattered disk objects are, in a sense, where comets come from. And people say, well, the Kuiper belt objects, sometimes come into the solar system, and these are the comets. Now they are icy. They're all icy, just like the other Kuiper belt objects. But it's actually kind of rare that objects from the Kuiper belt get dislodged somehow and come racing into the inner solar system, because they're really in orbits out there that are pretty stable, unbelievably so. And so when we look at the Kuiper belt objects, we don't know, what it would take to dislodge them. So we actually don't think that a lot of those Kuiper belt objects make their way in here to us. So where do we get our comets? Where do we get the asteroids that hit us, for instance? Well, the asteroid that hit us, for instance, is the one that at the Cretaceous Paleogene boundary 65 million years ago, hit off the Yucatan Peninsula. It's about 7 kilometers in size and made a 100-mile plus crater.
You could just say the dinosaurs.
Huh?
You could just say the dinosaur one.
Yes, I could.
As soon as you start saying, and I can't remember Crestio, Paleo.
Yeah, okay.
Yeah, I was. You say that on like dinosaurs, the one that took it, the dinosaurs.
But the fact that you knew that shows that you knew what I was saying.
I did.
You didn't have to wait.
I know, but just in case there's any newcomers.
Well, but you didn't let me finish my sentence.
Big words.
But finishing my sentence, I was going to say the one that killed the dinosaurs. That was the last thing I was going to say, and you took that away from me.
Now we're even.
That's fine. Anyway, yes, the asteroid that killed the dinosaurs and hit off the Yucatan Peninsula, leaving a 100-mile-plus crater, threw up a lot of dust into the air, and people think the dinosaurs died quickly, and that's not true. See, it was a cascading failure of ecosystems around the planet. Now, obviously, the dinosaurs in the immediate area of the impact were vaporized, all right? So whatever they were doing, if they were smoking in the boys' room, or if they were, running around in their hoods trying to get, all up in their other dinosaurs' grills, well, they were just going to be just eviscerated and destroyed by this incoming asteroid. So that said, there was some immediate death, but the real death came after this pall of smoke and dust went into the upper atmosphere and made its way around the globe. That happened over a period of years, months first, obviously, and then over a period of a couple of years, several years actually, that's when life forms began to die that depended on sunlight. All right, and when they did, then the dinosaurs that ate the plants were without food, and they began to die off. And then the theropods, the meat-eating dinosaurs that depended on the herbivores, the plant-eating dinosaurs for food, they began dying off. So it was sort of a cascading effect, and quite a large percentage of species died during that particular one, but that wasn't the biggest die-off. The biggest die-off was when 97% of life on the planet was destroyed, and that was, several 100 million years earlier in the Permian era, the Great Permian Dying, it was called. That wiped out 97%, and still life persisted. So that's really cool, and I think that's sort of the legacy of our planet. Life will find a way. And I've mentioned this before ad nauseum. Jeff Goldblum played Ian Malcolm, the scientist in Jurassic Park, and when they were talking about the raptors learning and so forth, he said, "Well, life will find a way," and that's exactly what happens here on this planet, and that's why they put that line in there. It was a scientific basis for that, not just an actor saying some kind of cool line. So it's a neat planet we live on. But also, if you heard one of our shows on KGRA on the SkyTour Radio, you probably might have heard the show where we said that Earth may not be the most habitable planet. Remember that one, Amanda?
That's crazy. Yeah,
isn't it?
That statement is hard to believe.
Right. Because we evolved into this.
It's scarier to think it's true. I mean,
we evolved into this, didn't we? We evolved into this. So because of that, we don't really know. We don't know what we're missing. We don't know what we don't know. So if we have, like we're here, we get skin cancers, and we have a planet that can kill us with earthquakes. We just live with it because we evolved into this. Well, maybe this isn't the way it's supposed to be. Maybe there's other possibilities for us that are out there, and that's the thing that we don't really know. So I'm pretty pleased that we have this on our side. We can use our science and actually find other worlds that might be better suited to us, and that better world is called a super habitable world, and the concept is super habitability. And there was actually a story which I read, and it basically said that there is another potentially habitable world that is actually, if it has exactly what we think it might have, it might be super habitable for us, a better place than Earth. Just amazing thought, isn't it?
It is.
Yeah. So, all right, let's head to our next object up for bids, and we're gonna go.
For the latecomers, can you tell us what we were just looking at?
Oh, there were some latecomers. Okay, sorry. Yeah, we were actually looking at a double star in. No, you're gonna make me look, aren't you? It's okay.
Make sure that we're all on our toes. So
yeah,
Canis
Venatici, it's a double star that we're looking at there, and it's really it's really cool. And there's another one here that is just beautiful. If you look at that one. All right, so let's go here. Yeah, with the moon being out, we like to look at some double stars because their color won't be compromised by the moon. But here's one that's just beautiful. Now this star is in Coma Berenices. It's also known as Struve, Struve, Struve 1657, but this is 24 Coma Berenices. It has a number because of the fact that that's the way these stars in this particular cluster were classified. This is actually a...
is this the 24th found in the cluster or something?
You know, that's never clear because it just...
Because that would make too much sense.
Yeah, that's true, actually. That's true. Well, let's take a look at these stars. Let's zoom in on these guys. Alright, there they go. They're gone. Thank you for coming. No, let me just bring them back.
Short and sweet.
Yeah, short and sweet. No, but this...
Okay, now that one looks more orangey.
That's right. That's right. And... The one on the left is a K0? K0. Let me look. I'm not sure. I think it's a K0. It could be. Let's find out. No, that's Earth. What the hell's that doing there? Get off of that. Yeah, 24. Yeah, 24. This is 24. And we're looking at K0 on the left and an A3 on the right. So we're looking at two beautiful stars. Now, what's interesting about this is it looks very reminiscent of another star pair we've seen, which are not the same types, but have similar colors, or very similar colors. And you might remember them. They're in our summer sky. So who remembers that the stellar pair we looked at before? Now, these stars are 2,780 astronomical units from each other. All right. So you know right away that since the other pair of stars we looked at, which looked like they had a similar separation, were only a few hundred astronomical units away. These are over 2,700 astronomical units away. That means that these stars have to be a lot farther away, and they are. This is this double star is actually 450 light years from our planet. And I want to just do a quick photo just to kind of see if we can capture the color a little better. So I'm going to dim it down just enough and then take a picture here. 50th of a second at 1000 ISO. And then we'll just jump in and see what we got.
Okay, so...
Look at that. You can actually see the colors very nicely there. But we're gonna do our trick too. Yeah,
wait. When we're measuring how far away the Oort cloud is,
yes.
Where are we counting from? The sun or Earth?
Yes, no, the sun.
The sun. Okay,
yeah,
and how far from the sun is the beginning of the Oort cloud, or the or it was like 26 point something, wasn't it?
Well, don't forget. Remember the Kuiper belt is after 30 astronomical units after
30. Okay.
After Neptune. And the Kuiper belt goes out to about 50 astronomical units. And then after that, it begins mixing with the Oort belt. And then the Oort belt goes out farther than that. And this is the impossibly crazy stuff to listen to and believe. But listen to this. The Oort cloud is rumored to actually go out 3.2 light years from our sun. That's literally almost to Alpha Centauri. It's 75% of the way to Alpha Centauri. And that's what the popular belief now is, that there's objects that are kind of loosely gravitationally bound to the sun as far as 3.2 light years away from our star. Now
so it would be 3.2 times 93 million?
No. A light year is 6 trillion miles. So it's 6 trillion times 3.2 to get miles. Then that gives you the miles. Then you divide that by the 93 million to get how many astronomical units that is.
Yeah.
So.
Silly me.
Yeah, no, that's not a big deal. I mean, it's just telling you. Okay.
No, it's just the one that the double stars we were looking at. There were just a few hundred. If that's from
Yes.
our sun class, the Oort cloud, and this is like over 2,000, you said?
Yeah.
So would that be like from the sun past Alpha Centauri then?
Well, just take 2,780 and put it into your calculator and multiply it times 93 million. Okay? And then you will get the number in miles. And then you divide that by 6 trillion to see how many light years that is. I'm walking around the dome with gloves on, so I can't really do that right now. But 2,700...
Yeah, I don't even know how to type those numbers into a calculator, so I'm not doing it.
Yeah, just keep hitting a lot of zeros. Somebody out there in the chat will. Someone in chat, do this. 2,780 times 93 million. That's 93,000,000. Alright? And then, that's the number of miles. Then divide that number by 6 times 6 trillion, which is 0,000,000,000,000,000. Right? You know, and see what you get for a final result. The number you get should be a small number, a singular number that will give you that distance in light years to that. Now, 2,780 is going to be a fractional number of light years. Okay? So, it'd be interesting to see what you get. There's people out there that are already doing it. I can tell. I can feel it. I hear the energy. Now, here's what I'm going to do. I'm going to defocus these stars just a bit because I want you to see the colors better. Look at that. Now we have that K0 star on the left, which is past G. Remember? OBAFGK. They're slightly more orange. And we do have that A star, the A3, on the right. So it's kind of a whitish star, which it looks at. Then we'll drop these back into focus.
Okay, it was 2780.
2,780. Yeah, 2,700.
I'm sorry, I don't know how to type these numbers. 2780?
Yes, 2,780 astronomical unit times 93 million. 93,000,000,000.
Okay.
And that gives you well, let's say, get that final number, get that value, and then you divide that by the number of miles in a light year, which is approximately 6 trillion miles. It's actually 5 points high number, 5.8 something, 5.9 something. And then that number gives you the fractional number of light years.
We have a guess from MMT, 0.04309.
Okay, yeah, that means he actually did the calculation. So
Kimbo says 43.09.
Well, it's not 43 light years, that's for sure.
Okay.
But see, this is what I like. This is so much fun.
You got people too curious to.
I love it. No, this is great. This is absolutely great. I mean, look, guys, that's what we're all about, man. That's what we're all about. We want to make sure that, I'm going to make sure I bring you things that you just wouldn't think about doing in your daily lives. And I don't have any idea why I'm out in the cold during my daily life. But you know what? I love what I do. Alright, so let's see now. We're getting some clouds moving in here.
0.43, yeah.
Okay.
And just for those that kind of got sidetracked on why we're even doing this in the first place, I was just wondering. I wanted to know what the distance was between these stars and how far it would be and whatnot, so.
Nice. And you did.
And now I know. Thank you. Thank you, everybody who actually did dig out those calculators. It's just... It's almost like I'm dyslexic when it comes to numbers, and I wouldn't even honestly know how to type that into a calculator.
Oh my!
I don't know how many zeros are in a trillion.
Okay, well, you know what? I'm glad for the honesty, and I don't expect that you know all these things.
This is why I
but this is
chemistry and biology.
But this is what makes you. This is what makes you who you are to everybody that listens. Okay. We like who you are. We don't want to see anything change. We don't want to have you change on our account. If you don't know it, that's fine. The fact that you say that is the honesty, which is phenomenal.
I would rather say I don't know than kind of make things up and try to fool people.
Exactly.
Wrong with not knowing. That's why I'm here every night, because
that's right.
I can have someone who does know and then find out, and then I will know. So
yeah, exactly.
That makes me pretty smart right there.
Yep.
Stick with the people with the answers.
Yeah. And there you go. Let's go to the next guy. Okay, this one is a little bit farther down in the constellation of Bootes, the sheep herder, or the goat herder, depending on what we're looking at there. And now let's pull it in. Look at that star. You can see it right now. You can see it as a beautiful double. This is one we haven't seen before. And this one, okay, let's pull it in here, move it up. Let's pop in and look at what that looks like up close. Oops, wrong way, Feldman. Anybody answer the wrong way Feldman question?
No, but it's a lot easier than those numbers, so who is wrong way Feldman? It does sound familiar.
Yes.
I want to guess it has something to do with baseball, maybe?
Nope.
Okay.
That's okay.
Sports? Is it sport related?
No.
Okay, then I'm thinking some kind of
I'll tell you.
video meme.
It's television related. Television related. TV series related, as a matter of fact. Now, while you're thinking about that...
I'm trying to think of any characters named Feldman.
Well, while you're thinking about it, let me just tell you what we're looking at. This is Kappa 1 Buddhist and Kappa 2 Buddhist. Now, Buddhist is the constellation, and Kappa is the Greek letter indicating that we are looking at a star that is not nearly as bright as the Alpha star, but is the Kappa star. So Kappa, K-A-P-P-A, in the Greek alphabet, brings us down. Okay, about 7 or so. Now, this is a very good double star. Shows up great in a small telescope, and has a bright white star with a bluish secondary. And they're separated by about 13.4 arc seconds. That's what you're seeing here. That separation you see between the two stars, that's 13.4 arc seconds. Now, this means that these stars here are with their separation, all right. And if I tell you that they're 676 astronomical units apart, all right, in real life, all right, which if you think about it, that's, Neptune is, 30 astronomical units. So it's literally over 20 times that distance, all right. So that said, we're looking at stars that are about 163 light years away, all right, 163 light years, just amazing, So I love the fact that these stars are in pairs, because you can actually get a really good feeling for what they are, and for their physical relationship with each other. I think that's pretty cool. So now the bluish star that we were talking about, that's an A8 on our spectral class scale, OBA. That's A8. So it's just before the F's. Before A8 is A9, then F0. And now we have this is an A8 there, and then we also have the secondary star, all right, which we talked about earlier. And that secondary star is, let me find him. We got the A8, and the A8, by the way, is what's called a subgiant. It's actually not it's not on the main sequence. It's not fusing hydrogen into helium anymore. It's probably doing helium into carbon and nitrogen and neon and so forth. Now the other star to its right and lower, that star is actually an F1. All right, so it's similar. It's not quite an F0. It's an F1. So this is an A8 and an F1 in a pair in a beautiful cosmic dance, which is going to go on for billions of years. The F1 star on the right is actually a main sequence star, so it's fusing hydrogen to helium normally, in the way that it does. And it's out there, like I said, 163 light years away and 676 astronomical units in separation from each other physically in space. So, any questions so far from anybody?
Just one that actually took me a second to figure out. I was like, did I zone out and miss Mark talking about something? But
what?
Now I understand. We may have an answer for Wrong-Way Feldman.
Oh, okay, great. Let's hear it.
Is it from Gilligan's Island?
Yes, it is! Well done!
Woohoo!
Oh, that's so cool. Yes. And it was played by an actor who was very good at making that, that sound like he was, like, what's going on? I don't know what's happening. What am I supposed to do? I'll be back for you, I promise. And he takes off and goes the wrong way. See, Gilligan's crew, they were all going to get rescued by Wrong-Way Feldman. And then he forgot where the island was that he came from because he goes the wrong way all the time. So they're almost there, but then not, But the series producers...
Well, congratulations to Tana.
Nice, Tana.
Because she said, is Mark talking about Gilligan's Island? And I thought, like, you were making an analogy to the stars or something. I'm like, I didn't hear him talking about Gilligan's Island. Did I zone out for a second? I'm like, oh, Wrong-Way Feldman. Oh, was he talking about Gilligan's Island? Okay, got it.
Yes.
Right
very good.
On.
Very, very good. Very pleased, Tana. That's a wonderful, wonderful...
Yeah. She was the only one. She was the only one that came up with that.
Well, maybe everybody else is sleeping and bored, so you know how it is.
Oh, she's on fire.
Yeah, that's great. That's so great.
I knew it sounded familiar, so I probably remembered the episode, but lost my memory bank.
It was out of your memory bank.
I can't even remember episodes of shows, and you're remembering all these details about all these stars and exoplanets and nebula and...
Yeah, well, I want to try and find these stars too, and we have clouds now, but I'm going to try and find this anyway, so we may not see it, but I'm going to give it a shot.
Try.
I'm trying. It's a little bit low. A little bit low in the sky. Okay, that's the star there, zipping around, and it should come back into view. I'm not sure if we're going to see it, but we'll try it. This star that we're looking at right now is a really fascinating star because it's actually a star in the constellation of Corona Borealis, and it's a star that's visual magnitude it's a variable star, so it goes from 6.5 all right to 10.78. Now your eye can only see to about magnitude 6 stars. Beyond that, they're all forever too faint for your eyes to see, and it's 68 light years away. Now the star actually is a double star with what's called a G0, and it's Roman numeral 5, so that means it's a G05. That means it's a regular fusion star, regular normal fusing star. And the other star is a G15, V. So these are actually two stars that are almost identical. So let's take a look and see if we can see the separation between them through the clouds here. I think you can kind of tell there's clouds because you don't really see a lot of other stars here. Here we go. Let's go see. Let's go see.
And just for the record, Robert also answered Gilligan's Island. I didn't see it.
Nice, Robert. Sorry. Congratulations. Well done. Let's go now. We're here. Oh, look at that. We can actually see that. Hang on 1 second, guys. I'll be right back to you. I gotta quickly answer a phone call.
Oh. Okay, and that's why he has a co-host. Let's see, I don't know anything about double stars, so I'll give a plug for the show. You can check us out Sunday nights on kgraradio.com. Sunday at 9 Eastern. That's 2100 hours for anyone in the military. It's called SkyTour Radio. It's a companion show to this, which is SkyTour LiveStream. Please hit the subscribe and the bell beside it so you can catch all the latest every time we go live. Sometimes we do try to advertise it on Facebook. Sometimes it's just for the moment if clouds break and Mark's up to it. He's actually in Connecticut. He's actually literally outside in a dome with a telescope bringing us all these views. And I'm cozy in my basement in Canada. So I watch the chat. I'm Danny Fan 1 in chat. My name's Amanda. So if you guys have any viewing requests you want to see, if there's a star, a planet, a nebula, something in the area we may be able to see, depending on the season, you can put that in chat. And if you have any questions for Mark, anything we're talking about, anything in general. Oh.
Yes, I'm back.
And here's the man of the hour.
No, I heard
Everything
that was
good?
very good. Yeah, everything's fine. But
and I'm extremely nosy, so I have no problem asking on air.
No, she has no problem with that. That's okay. Being nosy is okay, so as long as you're asking the right questions. You can see a little bit of discord between these stars because they're actually quite interesting. What a very interesting stellar pair these are. Both of these again are G stars, and so they are about the same color. In fact, they're almost identical in color. And they have that little thing going on, those little tiny spikes that we see. I'm gonna try and change the focus a little bit so you can see. The reason that's happening is because we're seeing it through clouds that are moving past them, and it's also because I think this is probably best there. Try that. And then what I'll do is take a photograph of these things as well. So let me take a picture. All right, and then we go in.
I like that sound of the picture being taken.
Yeah.
Even though it's a fake sound, I still like that sound.
I know. Well, it's important in the dark to know what's going on.
Of course.
Wow, look at those stars. It's just so interesting. Now, what I like about this setup is the fact that there's two identical stars, and they're separated by 160 astronomical units. So again, think of it in terms of Neptune, 30 astronomical units out, and how far away they are from each other. 160, right? So now we're talking about quite a distance here. If you do the math, divide 160 by 30, and you get how many times farther than Neptune these are from each other. So I think that's pretty neat, and I would like to, I guess just over 6 or 7, or 5 or 6 astronomical units. 5 or 6 times the distance to Neptune, but they're just beautiful. And
John has a really good question.
Sure.
And I was thinking about it earlier, but you know me, I jump all over the place here. So
I don't.
And that's why we're such a great pair. You'll actually go on these crazy rides with me. So
yeah. And
John
crazy it can be. Yes.
Well, I mean,
ask John's question. Come on.
Listen, you have the facts, and I just kind of dream up possibilities that could or could not be real.
Okay.
And you just tell me where I'm going wrong.
Changing the battery, by the way, just so you know. Yeah, go ahead. What's John's question?
Regarding double stars.
Yeah.
How weird would the orbit of the planet be? Because you talked about... No, maybe it wasn't Proxima. You talked about one the other night that orbits 2 stars. And was it? And it was a planet orbiting a double star?
Yeah, Proxima. Yeah, exactly. And that's called... And we talked about that on a radio show. It's not on a stream.
Oh, okay.
And a planet that orbits 2 stars is, farther out, and it orbits these 2 stars, which are orbiting each other farther in, and then it's on the outside orbiting both in a perfect circle. That's called a circumbinary orbit, and that's exactly what we saw with this star out there, which is really cool. It had a planet around it, and it was doing that. Really fascinating. Circumbinary.
But just because, if there was an exoplanet around a double star, it doesn't necessarily have to circle both of them, does it?
No, and the reason we know that's true is because we just have to look at Proxima Centauri. Alpha Centauri is a triple star system. It has A and B, which are kind of stars like the sun, sort of like these two actually. Okay, but then imagine a small, faint red dwarf circling both of those farther out, maybe halfway out. from to the edge of the screen and circling in an orbit around both of those. That's where Proxima is, approximately in that terms of that triple star system. And then Proxima has a planet circling it. So, I mean, the view from that planet around Proxima would be just spectacular. You'd have these two very bright stars like our sun in your night sky that would dominate the sky. And they wouldn't light it up like the sun at all. It would be two very bright stars. Kind of like having maybe two planet Venuses in the sky right near each other.
I say that.
I bet you did.
I don't know why, but I just did.
Yeah, well, it's just true. You know, that's sort of how it is. You know, two Venus-like planets next to it, and that's what it'd be like. Just an amazing, sight, and we're going to see these sights someday. Not us, perhaps, but we will. We will. Let's see now. Where is this one? I want to see if we can see this one. Okay, this might be difficult. Let me take a look at what the sky looks like. This is the one that I wanted to show you primarily. Let's see if we can see it. You're going to lose the one we're looking at right now because I'm moving the dome. Well, let's go here. Let's see if we can see it. This one's important to look at. It's cool to look at, let's say that. Okay. Alright. Now, maybe that's going to be alright. Let's see. There it is, down the lower left. Now, the first thing you'll notice is that the star we're looking at is actually just a very normal-looking star. We're not going to see a double per se, but I want to show this to you for a very important reason. And then let's see if we can find some more doubles to look at. But this is sort of like a one that we want to check out, and I want to show it to you for, again, like I said, a reason. So we zoom in on this, and all we see is a star. It doesn't look like much, all right? But what's fascinating about this star is, and this is called, the star is called 38 Virginis. It's actually in the constellation of Virgo, and it's in a location in the sky where it's nondescript. You wouldn't know the difference. You wouldn't notice it. However, the thing about it is that this is an exoplanet star. There is an exoplanet around that star. And I love showing these things to you because it's like, wow, we can actually see these. You know?
That's exciting. Yes.
It is. It really is. You know, it really is.
Can we see the exoplanet? I can't from this view.
Absolutely not. Never, absolutely not. No. See, and it has one.
Well, I had to ask. Come on.
Well, here's why this is so interesting. Okay, first of all, this star has one Jupiter-sized planet. All right, one Jupiter-sized planet, and the star itself is a very interesting star. It's about 107 light years from us. All right, and it's sort of a yellowish orange. It's an F5 with a Roman numeral V, Roman numeral 5. Luminosity class, right? And so the spectral type of the star is F5 and then V. So it's a normal fusion, hydrogen fusion star. But as an F, it's a little cooler than the sun. I'm sorry, a little hotter than the sun, rather. But certainly can have lots of planets around it. This one has one planet, and that planet is in the habitable zone. Now, it's a Jupiter-sized planet, so we think it's going to be a Jovian-type planet, a gas giant. But think about this. This is why I'm showing it to you. This planet, okay, 107 light years from the Earth, might have moons around it. And if those moons are anything like Europa or Titan around Saturn, Europa, Jupiter, or Titan around Saturn, then we could be looking at a system that might have a habitable world that's a moon.
Yay.
And that would put us in a whole new realm. Because we don't know about moons around any of these planets that we see. None. We can't detect them. You know? So, when we look at these, we don't have any idea whether they're going to have moons. But this particular star, 38 Virginis, in the constellation Virgo, 107 light years away, may very well have a habitable moon. Because that giant Jovian planet might be just the thing in that solar system, or in that system, that attracted all the deadly impactors to it. And they didn't hit the moons, they actually, hit the planet. Just like Jupiter, sweeps out our solar system. And if they did that, then that might give life a chance to develop. Imagine if it was like a Titan here. Titan has a heavy nitrogen atmosphere, and it's got methane ice and methane and ethane lakes on the surface because it's so cold, right? But there's lots of water, and it's locked up, hard as granite, under the surface and on the surface of that moon. Plenty of water. So, if a Titan was around this particular star at that particular location, then it would be a habitable moon. Titan's almost planet-sized, don't forget. So this means that we might actually be having to think and rethink how we think about extraterrestrial life, see? We might be thinking about this all wrong. We were looking for planets, but we should also be looking for moons. And that's the thing that this particular star is, important for, is that. And I'm going to just take a little photo. I'm going to actually drop us down to 1/8 of a second. And let's just take a picture. Let's see what we get. Okay, not enough. But if we look at it, we can actually see, we see just the star. But I want to actually have us, I want to see if we can actually pick up some more. I'm going to do a 1-second photo here. Now, we're not going to see an exoplanet. That's not what we're going to look for. Now, there are clouds over here. But here you go. You can see some of the stars now that surround it in this photo. There it is. Okay. All right, let me get the photo up. There's the photo. Let's get rid of this. Okay. So there's some of the stars. And now you actually see that star sitting out there in the middle of space with a known planet in a habitable zone. That planet that's in the not too hot, not too cold location around that star where liquid water can exist on the surface of the planet, if it's a solid rocky planet, or on the moons, if they're solid and rocky and have an atmosphere. And that's not so far-fetched, right? Titan has an atmosphere. So maybe one of these has an atmosphere. You don't know. We don't know. I'm going to do one more. Let's do a 5 seconds at 1,000 here. I mean, this is at 10,000. It's the moon is out, so we're gonna get a bright view, see, like this. But this gives us the idea of what we're trying to see here. And then we zoom in. I don't know about you, and to you listening, you guys, but isn't it kind of cool to see a star that we know has potential life around it? And this is one right here, and it would cause us to rethink all of life, the way it is because of the moons. But go ahead.
Well, I like that because, especially on KGRA radio, we do a weekly Exoplanet Roundup.
That's right.
And sometimes you'll talk all about the exoplanets and this and that, and then you're like, but then they're in the habitable zone. And I'm like, oh, well, that's disappointing. And then, you have this, it's like a gas giant. So again, it's like, oh, how disappointing. But then even finding some of these, finding the ones, smaller than Earth, is quite remarkable. And this, okay, maybe we can't live on the exoplanet, but the moons, that is even cooler than an exoplanet, I think, so...
That's right.
Just because all of them aren't in the habitable zone doesn't mean we're not getting a lot of incredible information from just discovering them and knowing what to look for, and
exactly right. And I think that's pretty cool.
We have a few questions coming in.
Sure.
Okay, Tana asks, are there any triple sun systems? What's the largest number of suns for one star system?
That's actually a very excellent question, because we found a lot of triples, many doubles, a lot of singles, and there are some quaternary stars where there actually is a very complex interaction. But as soon as you get more than 3, you end up with a situation where the physics is hard to work out, and it becomes what's called an n-body problem. N is in number. And the n-body problem is something that has been very, very tough to solve, and we've never been able to solve it, very easily. We can, but never very easily. Now, what I want to mention, though, is it's very interesting to consider that we also have to think about the fact that in a system that has more than 3 stars, the balance of gravity has to be so perfect that the slightest out of balance situation will cause one of those stars to be ejected, or one or two of those stars to be ejected from the system. Now, in clusters where stars form together, which is where they form, one of the things that we discover is that we find that these stars are usually double stars and triple stars, but seeing 4 together is only typical in young locations, stars that are young. And there is one place where there's 4 stars that is very, very popular. People know it very well. And while I go to the next object, I'd like you to think about what we're talking about. We're talking about a location where there's 4 stars that are sitting there that you can always see. All right? And these 4 stars are together in space. They're very close to each other. But they will migrate away in coming, millennia or, millions of years. But right now, they're together. Who knows that location? Let me know as I move.
Okay. Rephrase that so I can type it for them.
Oh, well, they're hearing me say it too.
Yeah.
All right.
What do you want? The names of the 4 stars or the location?
Well, when we consider when Tana asked about are there any stars that are more than 3 or whatever, yes, there is one famous quaternary pair that people learn in their early years when they're looking up astronomy and learning astronomy. That's actually very very famous location, and I'm wondering if anyone knows that set of stars. Okay. I mean, everybody in chat can also hear me, so they're getting the question anyway. Correct?
Yeah.
All right.
Yeah, right. No, well, we have, I guess.
Yeah, you're fading for me. You're not. You got your microphone far away.
Sorry.
There you go. Much better.
Is it possibly Sigma?
Sigma.
Oh, hold on. Like behind the horse's head? The horse head nebula?
No. That's sort of warm, but
The
we're looking.
trapezium?
Yes, the trapezium. Well done.
In
Who said
Orion
that?
Nebula.
Who said that?
Guess.
Daryl.
Yeah, Daryl. Woohoo!
Hey, Daryl. Nice job. Well done. See, you were in that crater I sent you that you didn't know you were getting. Daryl had loaned me a filter at one point, and it was a beautiful filter. A very expensive filter, and he didn't have to loan it, but he did. And because he did, when I finally sent it back, I also included one of our 3D printed craters for him, because he is just such a generous guy. Now, don't go asking him for the filter, guys. I'm just saying. Okay. All right, these stars, this is...
Give me a minute. You can actually... Hold on. I'm going to link the page on Facebook. You can check out the store where Mark makes these 3D printed craters.
Yeah.
And he has a UFO series of some famous, real or not. They influenced history.
That's right.
So
they have cultural significance, so I included them. They're the S4 UFO, the Area 51 S4 UFO, the Rex Heflin case UFO, and the Belgian Triangle UFO. So there's a Triangle UFO, a Heflin UFO, and an S4 UFO, and that's our History Maker series. And you can buy one or all of these UFOs online in our store. And of course, we have craters. You can also name your crater. If you don't see the crater in the list, whether on Mars, on the Moon, or even Pluto, you can ask us to send it to you or to make it for you, and we'll do that at no extra charge. We'll grow it, and we'll prepare it, and we will send it to you. And I'll tell you right now, when we took our craters, we had a stack of 16 craters, different ones, and we took them out to one of the conferences that we attended just recently. And it was a conference that had an awful lot of people with 3D printers there. It was sort of an industrial thing. And the people came over and looked at our craters, and said, "How the heck did you get these to look so good?" It's because we have a special process to actually get rid of those little jaggies that you see in a 3D print. But see, most people use like solvents to kind of melt those jaggies. The problem with that is that it ruins the data. It ruins it. It gives you false data. And what we did is we actually fill in those jaggies, and then we use solvents, and the combination of the two gives us a result that is unbeatable. And we make molds of the final result, and then we produce those. So that's how we actually make our craters. So it's not just a simple 3D print and off it goes. We do an awful lot of work with them before we send them out there. Okay. This particular double star.
Back in chat. Sorry, listen. Can we see the Terra Mura system?
The who? What?
What's that? Terra Mura.
What's Terra?
TERAMURA.
I don't know what that is. Terra Mura. What's Terra Mura?
I don't know, but Tana asked if we could see it. Tana, do you know the location, or if there's any...
Tana, get your butt over here and show us where that is, please.
Mm-hmm.
Yeah, we're a little chilly here. First of all, just so you know, this is 16 and 17 Draconis. They're two stars next to each other. And they're actually about 410 light years away. They're separated by 89 seconds of arc. So 89 arc seconds. And they are also a very, very nice pair of stars. And their spectral classes are that they're both white stars. Okay. Now, well, actually, whitish, little blue. They're actually B9s. And it's the other thing too is there's actually 3 here. But the problem is you can't actually see the other one. And I'm trying to figure out where this would be. I'm trying to see like on the angle on the screen where it might be. We're about as far in. We're actually as far in as we can get. If I come back out, maybe not. We can actually go a little further. How about that? Okay. All right, now we go. Let me see if we got this. Hold on. I thought we were already zoomed in. My apologies. Okay. Well, still. Interesting because there's also what?
Okay, sorry. Tana just sent me what she was looking for. It's 30 Eratist star system.
Oh, Arietis? ARIE?
Probably. Yeah.
Oh, okay.
I didn't see the eye, sorry.
That's okay. No, actually, we cannot see that, unfortunately. Can't see that here. That's too bad, because it's actually pretty.
Can you tell us about it? I've never heard of it, but I guess she was, she's been doing a lot of work on her own, really looking into these things, and I think she's really enjoying them too, so... Yeah, she just sent me just a little link of what she was looking at. So, what is that?
I don't have. I mean, I can actually. Let me finish this one first.
Okay, sorry.
Okay, that's okay. You're asking me, okay, and it's fine to go in 10 different directions because it's just exciting stuff. I think I said these. This is actually what we're looking at here are actually 3 stars. And we see 2, all right, that are very clear. But then we have another one. If you notice, the upper one kind of has an oblong look, and that's because there's a second one in there. And it's actually, they're very close to each other. And it's the other one down on the lower right, that's the one that's like 89 arc seconds away. And then the top stars are only a couple arc seconds away from each other. But they're B9 stars, so late B, and very, very interesting because of the way they interact with each other. So this is an example of a triple star system that Tana was talking about. That's why I wanted to get that done before we went on, because it's exactly what she was talking about. But not precisely. It's 3, not 4. You know what I mean?
Yeah. Well, I don't. The one that she was specifically looking for, I don't think that was a 4-star system. I think that was maybe just something else, but Just in general, anything more than 3, yeah.
Yeah.
So, that's very cool.
Right. Yeah, I can't find my info on 30 Arietis here, so I may have to wait on that. I don't want to.
Sorry for the interruptions.
I don't want to. No, that's fine. I don't want to lie. That's the thing. I don't want to lie and tell people something that I'm not really quite sure of. And I don't fill my head with factoids. I actually just and that's, I know it's hard to believe, but I do fill my head with factoids, but not all the time.
I know, and it's just so much. I just assume, regardless of what I name, you'll know the location. You'll know if it's in season, if we can see it from this hemisphere.
Yeah, no, I know.
I'm just like, ooh, what's this?
And there's nothing wrong with that. Nothing wrong with that. I mean, that's okay.
But then I put you in a position when it's like, oh, I don't know this one. It's like, oh.
That's okay.
You can't know everything in the entire universe,
well,
by name.
Daryl does.
No.
Daryl's really good.
Daryl's amazing, yes. And I think he's basically agreed. We hope to have him on SkyTour Radio one evening.
Absolutely, if he wants to go on. I'd like to have him as a guest. I think he'd be very good at it. Very good.
Oh, I know he would be, yeah.
Very good person to talk to.
Well, rumor has that we may be getting that second hour people have been asking about.
Where'd you hear that? I didn't hear it. Tell me what did I miss?
I'm pretty nosy. I hear things. But anyway, but it's not official. It's not official, but hopefully it is in the works. And I think then we will really be able to open lines for people to call in with questions or share stories, or if there's a interesting article you've read that you want to discuss, or so that'll definitely open up a lot of possibilities for the show.
Oh yeah, absolutely will.
But until then, you'll have to deal with me reading the questions for you on your behalf, listeners.
That's okay. That's I understand.
Opening the lines might put me out of a job. Maybe we shouldn't.
Oh, the heck it will. You're gonna be busier than ever. By the way, as we're talking here, I'm remembering some things about 30 Arietis. They also call it 30 ARI, and this particular star is about 130 light years away, kind of like one of the other ones we're just looking at, and it's 4 stars. It's a quaternary system, just like the trapezium. But the problem is that it is, but it isn't. You can't see it. One of the stars actually has a spectroscopic binary, and that's the reason I'm remembering this. So, what's a spectroscopic binary? It's a binary star, a true binary. It's a binary with another star orbiting it, but the star is so close that the primary star that's overwhelming in brightness, and the secondary star might actually be sharing material between them. That doesn't make them a spectroscopic binary. It just means they could be so close that could be happening. It depends on their distance. If they're far away, then a spectroscopic binary doesn't have to be in contact or nearly a contact, what we call a contact binary. But if it was only, say, 10 light years away, then, and being spectroscopic, then it might be some kind of star that's very, very close to the star and might actually be sharing material through that central point, that common center around them, the common rotation, common binary orbit there, the barycenter, as it's called. So, as far as what 30 Arietis means for us, okay, the thing is, remember I talked to you about how these young systems will change over time? 30 Arietis is only about a few 100 million years old. It's not very old. It hasn't been around for billions of years. It's only a few 100 million years old. So we will find that those stars will move away from each other over time. They absolutely will. And that's why right now they seem odd. They seem like a quaternary system now, but they're not going to be forever. And that's the thing I do remember about 30 Arietis. And I know that if we could find it, I would love to see it. But I'm going to try.
Yeah, the link she sent said an enormous planet was found to be in the quadruple star system.
What's what? What did you say?
A planet, an enormous planet.
Oh, yeah, probably.
Was found in the quadruple star system.
But it's only circular. It's only, I'm not sure which what the layout for Arietis that is.
It looks like it's going around 30 ReB.
Okay, capital B, you mean? That's
capital B, yes.
Yep. Okay. All right. So.
Okay, well, I figured that would mean something to you. I posted a link
in chat,
so if people want
to. I told you what I remember.
Yeah, I know.
Yeah. Now, see, the problem is the star is not visible to us right now. It's in Aries, so Arietis rather. So let's see, it's Aries, so we won't see it. It rises at 5 in the morning, actually, 5:44. So let's hang out and wait. But it's gonna actually
Hopefully we'll all be in bed by then.
Well, it's gonna be cloudy and raining before then. So I'm squeezing in a stream before the rain here. So I hope you guys understand that I'm trying to do my best here with the weather that's sneaking in on us.
Oh, we always appreciate your streams. And so many lately, too, really making up for lost time. Hey,
hell yeah.
Get the clear skies and the nice weather, do it.
That's right. I'm not going to give it up. I mean, yesterday I went out and, yesterday was clear, too, but you know what I did yesterday? I came out here and I just did photography for everyone so they could see the things we saw the night before. Remember I told you I was going to do that? That's what I do. I make sure that...
He did that after the radio show. So
I did.
After we went live, he went up to the scope.
I did.
By himself, in the cold, in the dark.
Yeah, I had to. I wanted to make sure that I had something to show folks, Now, let's go to this other star right now. And it's right near this one. Not far. Let's see if we'll see it. This is... Yeah, we do. It's another double star.
It's crazy to think tonight, like, you can just move your telescope just over a bit here, a little bit there, and landing on all these double stars, like, you'd think, like,
it's not
so
hard.
Random,
they're right.
So far away, but no, these things are everywhere.
Oh, that's right. They're right nearby, That is in the sky, in terms of the sky, yeah. What do we got here? Alright, let's see here. Alright, how come I should be able to see this? Maybe I'm not seeing where I think I'm seeing. Oh, is that it? Oh, I guess that's down there. No, it's not bright enough. There's something else. Oh, the clouds are killing us. I'm trying to see why I don't see this. I'm trying to. The reason I did this is because it has a real interesting name. And I'm going to take a photo now, just 5 seconds at 10,000. It's going to be kind of bright because it's looking through clouds. But I want to see if we can see what I want to show you. Yeah, no, apparently not. I don't know why. Stars.
The double.
Huh?
I don't see the double.
Yeah, no, I know, but we should. That's the thing. The double is actually pretty obvious. So why would this not
star
show
be
me?
behind it? I guess not.
Let me try this again. No.
How often does that happen? How often does that kind of orbit happen when the stars go behind each other?
Well, it would have to be it would have to be something that we can actually see, but we really can't see something like that. Wait a minute,
well,
maybe
we would see it at its sides, and
yeah, but we wouldn't see it orbiting because stars sometimes take, thousands of years to orbit each other, so we wouldn't see that. All right, let's see here. Maybe I went to the wrong place. No, that's it. That's fascinating. I'm gonna have to check the data because theoretically there should be a star to the upper left of that star right there. So I don't know why it's not there. And my first thought is to think, well, maybe I'm not in the right area, but I am in the right area. Or maybe it's actually, what's the separation on these? Separation between the stars is 2.6 arc seconds. Oh, okay. Makes sense. Okay, yeah, no, we couldn't see it yet. I might be confusing this one. This star actually has an interesting name. It's the only reason we went to it. How many people saw Dune out there? You remember Dune, the actual, the movie Dune, Frank Herbert's Dune? One of the planets, not the star, but one of the planets was named Arrakis. And that's what this star is named, Arrakis. It's actually, I was just kind of wanted to show you that one. It's now I understand why we don't see it. Oh, the Blue Danube is playing again. Every time the Blue Danube plays, it's like, okay, it's time to go. All right, let's see here.
You changed the playlist around a little, didn't you?
I thought I did. You watched me. All right, let's see what's going on here. I'm going to try to see another one. Okay.
I have some more questions coming in. This
Sure.
one was from Ronald. It was back a little bit when we were talking about that Jupiter-like planet with the moons that could be habitable.
Yes, exactly.
Ronald wanted to know, how can you tell if there are more bodies like moons?
Well, that's the thing, okay? Maybe once we can see the planets more directly, then we can tell whether the planets are wobbling in their orbits. And if they're wobbling, then it means that something's tugging on them, and that something would be planets, of course. Now, that could be hard, but Jupiter does a little dance as it orbits the sun. It's moving all over the place, making little squiggly moves, and when we look at it in, like the universe simulator that we play with sometimes, we watch it there, and we can actually watch the wobble and see the wobble, and it's accurate. It's pretty accurate. It's beautiful. Now, let's go to this guy here and see if we can see something. I'm going to go just a little bit farther away to yet another double star. There it is. Okay, that's pretty obvious.
Yeah, that was easy.
Yes. Well, yeah, I'm trying to make it so that we get as much in here as we can while we're waiting here. Oh, wow. That's funny.
What's so funny?
I realized what just happened.
What just happened?
We're seeing... Okay, okay, that other star we just saw is the one that I thought we were supposed to be going to, which was Arrakis. And we only saw one, right?
That's right.
Well, then we go to this other star, Coma. All right, and Coma is Coma, K-U-M-A.
Coma, okay.
Yeah, and Coma is a very easily seen double star, and we see it here. It's beautiful. So I think what I was confused with this star system, and thinking I was looking at the other one. So my mistake on that. Now let's just get out of here for 1 second. Just bring this up. These are beautiful double stars. Now, the data on this one is interesting too. This double star is 98.7 light years from the planet, from us. All right, and this is what's called a circumpolar system, meaning it never sets. It's so close to the pole that it doesn't set. All right, it just goes around and around and around the pole. It's always visible from here. All right. Now, both of these stars are A-class main sequence stars. So we don't know. It might be that it's about like an A6 pair of stars. Okay, and they're Roman numeral.
Both are A6.
Yes, and it's like a Roman numeral, V for normal hydrogen fusing. And I always avoid using the word dwarf because no one thinks stars are dwarfs, right? Except we call these stars dwarfs. These are dwarfs. Dwarfs meaning, don't ask me why that came to be, but compared to some of the other giant stars out there, these are certainly dwarfs, all right? And these stars are A6 dwarfs. So that means, when I say dwarf, it means they're a main sequence. That means they're on that little snaky line that Ejnar Hertzsprung and Henry Norris Russell found when they mapped temperature versus brightness opposite each other, they found there was a bunch of stars that followed this snaky line from the upper left to the lower right. And that snaky line is what came to be called the main sequence. And come to find out, it was stars that were actually fusing hydrogen to helium in a normal manner. And that's why we call these dwarfs and the main sequence. So these are A6 dwarfs that we're looking at right here.
Can you compare stars to planets, like size? Because I know you said brightness matters in what the star size looks like, but like, could you say these stars are smaller than Earth? If they were, for example, like, could you say like an A star is smaller than Jupiter and a G star? Well,
I mean,
not all G stars are
what do you mean? What do you mean by that? Because there's no normal stars that are smaller than any planet whatsoever, even Jupiter. So they're all much, much larger. Even the smallest M star.
And that's why Jupiter is a failed star, right?
No, it's not. It's not a failed star. I hear that a lot, and I'll tell you why it's not a failed star. Jupiter is just a Jovian planet. All right. There's no failed stars. That implied it tried to be a star and it never did. It was never on
I don't know where I heard that term, but no, I heard that term.
Yeah, you have, and that's unfortunate because, you know, that's like saying Earth is a failed super Earth. You know, we were made our size because that's how much material was available. All right, and there goes a Lyrid. I just saw a meteor, but that doesn't make Earth a failed super planet. You know, super Earth. Okay. And in the same way, it doesn't make Jupiter a failed star. Jupiter would have to be 80 times bigger to become the smallest of stars. And the fact that it's 80 times more massive, not bigger in diameter. So 80 times more massive to be a star, even the smallest. So, and that would be an M-type star, you know. That said, Jupiter isn't even close to being what's called a brown dwarf, which is a substellar object. So not quite the mass needed to become a star. You know, that's what the brown dwarfs are. I mean, awesome, but still not quite a star at all. You know, is there more questions too, by the way? Because I'm thinking about going to another object here.
There is, but this one isn't necessarily about these double stars.
That's okay, go ahead.
Tana wanted to know, what is the fastest moving object in space that we can actually see moving?
That would typically be a comet or an asteroid. Now, I don't know if she was with us on that stream we did last year where we looked at Comet Holmes. And as we watched Comet Holmes, we actually took a picture of it at around like 9:30 or 9 p.m., and then came back to it at 11, and we saw that it was in two different places just in that time frame.
That was one of the few streams I actually missed.
Yeah,
I was going to say a year ago. How could anyone remember a year ago? But
oh, you remember the comet? You remember the comet?
Night you I remember missing the comet. Yeah.
Yes, night of the comet.
Yeah, you guys caught it. Yeah.
Yeah. Pretty cool.
Well, serves me right for sleeping.
Well, you're allowed to sleep.
Yeah, but then I'd miss things like comets.
Oh, hardly a problem. Alright. Now, let's just go to this other guy here and see what we can do here. Yeah, this is looking into clouds, so I don't know how much we're going to see here, but let's give it a shot, shall we?
Slam Stunk says they remembered reading something on, is it IFL Science, I know them, about a purple star. Do you know anything about a purple star?
Well, we got to be careful when we say purple stars. There's really no stars that are actually purple, but there are stars that have a light down in the purple end of the spectrum, and that's because they have a lot of ultraviolet light that they're giving off, and that might be what he's talking about. Okay.
Possibly.
Yeah. This is
Admiral Mark is back wanting.
Hey, Admiral Mark, what's going on?
I think he was recommended from P&K Space Imaging, but I'm not sure.
I think he was. I mean, and I think he also subscribed to SkyTour LiveStream. Thank you, Admiral Mark. I believe you have.
Wonderful. Glad you're back.
No.
He wants to know if there's any black holes we can see, which is always a great question.
It is a great question because technically everyone knows we can't see a black hole directly, but we can see what a black hole does to the space around it, but not with a regular telescope, unfortunately. To see that, we would need a radio telescope or a gamma ray telescope, something that can see those high energy emissions coming off of a black hole. Incidentally, this is a double star in Hercules, which is kind of interesting because you can actually see the very faint star right to the right of this main star. Do you see it?
I see it.
Yeah. This is called Delta Hercules. It's in the constellation of Hercules. The star's name is Sarin, like the nerve gas. Okay, Sarin though. And it's distance between these two stars. Believe it or not, they look like they're right next to each other, but the distance is almost 300 astronomical units. So 10 times the distance to Neptune. Okay, is how far away these stars actually are. All right. So, it's 75 light years away, too. So, when it's that far away, they can look really close,
See, the littler one, kind of the top right.
Yeah.
I know maybe it's because you put the suggestion in my head. I would say that one might look a little orangey. And it looks like, rather than them being side by side, it looks like it's back really, really far. But again, it's probably the brightness that's throwing it, That's confusing me anyway. You probably understand what you're looking at, not me.
No, I'm actually impressed because that star is actually an F0. All right, so it's more of a white. Okay, it's just after A, right? So OBAF. All right, it's an F star, and it looks orangey, probably as an artifact here, because the star to the left is a little bit bluer looking, right?
I see, and that's why.
Yeah.
Am I actually seeing orange, or is it just because that idea is in my head now?
Well, probably because it's in your head, but that's okay. I mean, fainter objects will look a little bit, more toward the red, Yet this star is actually, more of a white star. The primary is. So it's kind of cool. It's neat. I like these two stars. They look really, really pretty together. And I'm trying to find what we want to see here. I'm trying to find the actual. Okay. So the reason that star is so much brighter, though, on the left, is an interesting one. It's an A3, okay, so it's a white star, and it's 3 levels into the, or 4 actually, 0, 1, 2, 3. It's A3 into the A class of stars, and it's also a subgiant, meaning that it's not a main sequence star. It's actually a subgiant, meaning it's moved off the main sequence already. It's done fusing hydrogen into helium, right? So it's moved basically up on the diagram, and that's why we see that it looks so bright. That means it's a lot bigger, all right? And so being much bigger, it will have a brighter luminosity, that brightness that we see. And that bright luminosity is something that makes these stars look like they're mismatched, but in fact, they're A's. That's an A star there, and the smaller one's an F. So not too far away from each other, but one has moved off the main sequence. They were probably both the same size at one point and probably similar brightness. But now, as this star on the left has evolved, used up its hydrogen, it begins to collapse a little bit. And when it collapses, the temperature in the core of the star gets hotter and hotter under higher pressure, under that gravitational pressure, squeezing all that stuff into the core. When that happens, the temperature increases to about 100 million degrees Kelvin. And when that happens, the helium that was left over from the hydrogen to helium fusion process originally, that helium starts to fuse into carbon and other things. And when that happens, the star gets a newfound material to fuse, and it bloats again. And depending on the mass of the star, it can do this a few times and make more and more elements in its core. So it'll still be fusing hydrogen outside the core, in the outer areas of the envelope of the star, as we call it, the outer atmosphere and inner atmosphere of the star. It'll still be fusing hydrogen into helium, but then it'll be fusing other elements in that outer core and inner core, and it'll be like helium going into, like I said, neon and other things, oxygen and so forth. And so that said, the star will continue to bloat and get bigger, smaller as the fusion elements, the fusion fuel wanes, and then temperatures change to allow further fusion to occur. So it's really an interesting system that someday might see that star on the left gone in a supernova. Now, that may or may not happen, but if it goes into a supernova, then it'll probably only get as far as a neutron star. It will never be a black hole. It's not massive enough for that. All right, and that star on the right could fully survive it, because keep in mind, it's actually quite far away in real life. All right, the other star is just brighter, so it looks brighter in our sky to us. Remember, so when we look at that star, remember, it's almost 300 astronomical units away, 10 times the distance to Uranus. So the supernova won't affect this star most likely. And we've seen a case, in fact, we covered it on our show, our KGRI radio, SkyTour radio, the other night. And it was the case of a planet that was circling a pulsar, which is the remnant of a supernova explosion, and a white dwarf, which is the end state.
Oh my god.
Remember that? The end state.
Was that PSR?
Yes.
1820 to 26A?
That's the one.
Dude, how good is that, eh?
Yeah.
That is such an obscure name.
You're far from your mic, though. Get closer.
Oh.
Get closer to your mic.
Well, I didn't think I moved it.
There you go.
And I'm screaming, so. I'm very happy that I got that, because I didn't realize it was a pulsar. That's why the PSR, I just figured was a different catalog, but then such an obscure number with a dash, like 1820-26A. I was like, okay, this is the whole system. But
was it 1820 or 1620?
I thought it was 1820. Maybe not. I could be wrong. I often am.
That's right. Well, what's interesting is about that star we were just talking about, or that system, there is a planet, like a Jupiter-sized planet, and it's orbiting, as we just said, the remains of a supernova explosion, which is a pulsar, which is a rapidly spinning neutron star, and this one is rotating 100 times per second. All right, pulsar. Now, that's a star that can be anywhere from just a few miles across to a few tens of miles across. The white dwarf can be about Earth-sized or so, and the pulsar, we know it's a pulsar because it has a spinning, has a hot spot on its surface that's giving off high radiation, and that rotates so fast that we see it. And when we see it pass by us, it's like a lighthouse beacon in the cosmic night. You know, it's just flashing us with this high radiation from a long, long way away, so it's not deadly. And it's just like, but 100 times a second. Now that is a huge amount of spin that was imparted on the core of that star during this explosion. That just gives you an idea of how massively powerful a star is in general, that when it explodes, it can actually spin its core so fast. And as we said in a radio show, that 100 revolutions per second for the core of that pulsar is actually not even the highest. In fact, it's 1/7 the highest. There's well over 700 revolutions per second on some of these pulsars. That's huge. That just gives you an idea of the mass of the original star. Now, here we don't see that. We just have a subgiant on the left, and we have an F0 star on the right. And the left star will go away in a supernova eventually, but we don't know when that'll be. We don't really get warning signs, so to speak. But I just think that's a really cool, a very cool set of stars that we're looking at here. unfortunately, our clouds are now really making it difficult, and we're not going to be able to even see anything with any kind of clarity anymore. So, sadly,
did we view a pulsar, or
no,
maybe not now with the
no,
clouds,
we can't see a pulsar. No, we can't really see a pulsar because the pulsar requires a telescope that can see in the light of the radiation that's being given off by the pulsar. So we'd have to see it with an X-ray telescope or something like that, and we can't see X-rays with this. We're not going to see that.
Be really good and talk to Santa in December.
Oh, yeah.
Wait, do you want an X-ray telescope?
No, I don't actually. No? I would actually because we really can't see them from down here. We can't. X-rays aren't going to get down to us. In an effective way, just like ultraviolet doesn't come down in an effective way. We get some, all right, and we get infrared too, but we don't get enough. You have to be on a really high mountaintop for it to have any kind of potential capturability to see it. But what I'm going to do now, though, is take us to one last object we started with and finished with, our lovely moon. So I hope you guys will be happy with the last view that I will give us for tonight, and then I'm going to end the stream. I hope you guys had a good time. If you have, please let us know, because I would love to know what you think of our streams.
Share with your friends.
Yes.
We do have another question, and
please do.
It's so sad because you would think I should be able to answer this by now, but
I wouldn't necessarily know. You tell me. What is it? Is it a question you think you should answer?
I should know the answer. Not that I should know the answer. I should know how to be able to explain the difference. But
okay.
Maybe you explaining it one last time will help me really, really get it.
All right.
Tan wants to know.
Yeah.
Well, the first part I could take a guess, but it's a two-part question. How can we tell where a meteor shower is coming from?
Where a meteor shower is coming from?
Yeah.
Oh, I have no idea. No, I'm just kidding. Well, first of all, enjoy the bright white. Sorry about that. This is what happens when you're looking at the moon and highly sensitive, and you're in this highly sensitive ISO. Okay, so let's go down to 50 ISO and go down here. We're looking at the moon through some clouds here. The way you actually would know where the meteors are coming from is by something called the radiant. Radiant. That's R-A-D-I-A-N-T. Radiant. The radiant is the location that they all seem to be coming from. If you drew a line back along where you actually saw them, then that radiant is actually a place where all those lines overlap and where they come together. And the radiant is something that would also be a very good place for you to start looking for the source of the meteors. And the source of the meteors might be that it's always a comet that has passed by earlier, and that is earlier could be decades earlier, and it leaves this dust trail in space, as we talked about. And the dust trail that it leaves behind is what we end up seeing all over the solar system. And that dust trail is the thing that ends up filtering into our atmosphere at one point or another. And when it does, we end up seeing this tremendous amount of meteoric dust that hits us. The thing about meteoric dust is that this meteoric dust, I'm focusing, is actually very fine. It's only about the size of a grain of sand, each meteor. Hard to believe, but it's true. Now,
that may kind of be answering the second part of the question too, which was what the difference between an asteroid and a meteor is. Okay, so a meteor is a piece of sand that comes from a comet, and an asteroid is something that comes from the asteroid belt between Mars and Jupiter.
That's correct.
But the comet is further out than the asteroid belt.
Well, not necessarily. I mean,
Not
obviously,
necessarily.
the comet had to reach us and go through space, and so somewhere along Earth's orbit, the dust tail of that comet left particles that we pass through. And then when we pass through them, Earth's gravity pulls in some of it a little at a time each year, and we get that. We get these meteors, and that's something that we see as the meteoric dust that comes in. Really, it's good stuff. This is great astronomy when you talk about this stuff. Incidentally, in this crater,
that was always a problem I had, but we actually did do a show on SkyTour Radio. That's why I was thinking I should be able to explain this one, but
it's okay. That's okay.
Yeah, it's on the right track anyway. So
yes, you were.
Hopefully that helps explain it. I think it was 2 episodes ago, Tana. You can check the archives. They're free. Anyone can have access to them at kgraradio.com. Go to the archives.
Yep.
Past episodes.
Absolutely. And then go there and witness all of the splendorous shows we've done. It's pretty cool.
Tana says, do they both have an orbit? That's why we have certain showers, right? That's why we know, like, the Leonids were last weekend, because we can time these things now, right? We can time...
Right.
Is it the comet going by, and then the dust falls and we see
keep in mind that when a comet comes by, it has an orbit, usually an elliptical orbit. If it's a periodic comet, meaning it comes back, Halley's Comet has an elliptical orbit around the sun. The comet goes out just past Saturn or so, then comes back every 76 years. That's Halley's. But then, if we're talking about other comets, some comets don't actually come here more than once. All right, and those have parabolic orbits. They come in and they go out, and then they're gone. They go way back out through the Oort cloud. Maybe they have enough momentum to carry them away and out of the Oort cloud, but maybe not. Anyway. These comets that come through have an orbit and of some form, and all along that orbit they're shedding dust. All right, because that's what comets do. They actually do what's called outgas. They send off jets of gas as the sun heats them up, and every time they do that, because they're so small, they don't have strong gravitational force, and so they shed all this stuff. Think of Pigpen in the Charlie Brown series, where everywhere Pigpen walks, he leaves a dust cloud behind him. That's exactly what's going on with comets in real life. They're leaving dust behind them. And that dust becomes the meteor shower later on, because we will drift into that old tail of the comet, sometimes 100 years later. All right? And when we do, we see these meteors. And like the Leonids, there have been... the Leonids, which is actually kind of right now actually is the constellation that the moon is in. It's in Leo right now. Right where the moon is pointing, the Leonids have every year in November, I believe, they have a brilliant meteor shower, because there was a fairly dense knot in the dust tail from the comet that passed through there years and years and years and years ago. Okay, decades ago. And that comet left enough debris so that every time we passed through it, every time Earth passed through that dust tail, this material would rain down and be pulled into the Earth's atmosphere. And in the 1800s, people saw hundreds of meteors an hour. Hundreds. So it's like there were several a second, in fact. And the rate got extremely high at one point. And people thought it was the end of the world. They began to worry, because literally looking up in the sky, all they saw was streaks. Everywhere they looked, And that didn't last always. And in fact, the next year it didn't happen the same way, and it hasn't since. We haven't seen that kind of frequency. Why? Well, because the Earth effectively scoured that area of space free of that material. Now, the dust cloud is moving slowly. It's being pulled by the sun, of course, and it interacts with other planets, and these little particles get moved around, Earth especially. And so maybe there'll come a point where we'll pass through this dust tail again and see this tremendous display again. But right now we don't know, and we can't really predict. And incidentally, I just want to say, if you look in the crater here in the center, you see that the top of the crater is fully illuminated. The rim, you see that? It's got a perfect circle. It looks like an ellipse from here, but it's in the dark area of that crater, and I just think that's beautiful. That's why I left it here, and that's how we'll close. But any questions? Any questions left there, Amanda?
I think we got the one.
Yeah. All right. I want my winter here to stop, man. It was almost 68 degrees here, but today. But because of the fact that we have still got a lot of cold weather here, it does really affect me greatly. I don't like it at all. Sorry. Let me just try something. I'm gonna drift this over. I'm doing a little thing that I used to do. I used to take the actual dome in an observatory that I worked in, and I would move the edge of the dome over the moon. So what I've done here is I've actually reduced the amount of light entering the telescope, because I have almost the entire telescope blocked by the edge of the dome, and then I could go a little further and you see, and it'll finally go away. But to do that, you actually can get a better view without touching the camera. You can actually just reduce the light and then bring up the light by going back to moving the dome around, which is kind of cool. See? Just a little stupid thing that I like to do, And now, see, it almost looks too bright. But we can see the crater again, which is really nice. Cool. Well, anyway, guys, I really want to thank you for hanging out with me once again. It is 11 o'clock, so we did a 2-hour stream tonight. And this is perfect, because the clouds came in at just the right time to completely ruin our fun. So I will be talking to you again, and I'm not sure when that'll be. It'll depend on the clarity of the weather. But I can tell you...
That's the only problem. That's why you have to hit the bell to make sure you catch the live streams.
Yep,
because
that's right.
It all depends on the weather, so we can't say a certain time on a certain day. We can just cross our fingers and hope for the best.
Yeah, we can't. We just have to just let it be. Let it be, let it be. So that said...
I know. Let it be.
Yeah, that's kind of why I said that.
I know.
I said that for you.
I appreciate it.
I said that for you. Let me just... Now, for those that are listening, what's funny is... I'm going to focus again here if I can. What's funny is if they were here yesterday or the day before, they heard this song as well, right when I was closing. It sounds like that end of the Saturday Night Live where everybody's standing there waving and, just leaning back and forth. It's like, oh, we'll see you again next time. Thank you so much. And thank you to our host, blah, blah, blah. And that's kind of where we are now. It's kind of funny. But, guys, I want to thank you guys so much for coming out and spending your evening with us. We appreciate you like you can't believe. You're great people, good friends. Your
continued love and support that keeps us doing this. So,
yes.
Great questions,
Absolutely.
Great suggestions on what to look for, and
yep.
Yeah, let's do it again soon.
Indeed. And we will talk soon. So, hopefully, and I will make sure that I hit stop streaming tonight.
I'm going on mute until I see stream is offline, so...
For those who weren't here yesterday, maybe you were, I thought I hit stop streaming last night, or the other night, when we did this, and I didn't. I did, but the mouse needs to be replaced out here, so it didn't actually, we heard the click, both Amanda and I heard the click, but it didn't stop streaming. And then I noticed it didn't stop streaming, and I moved I moved the screen down so that the stop streaming, which said start streaming, it didn't say start, it still said stop streaming. The stream was still going. So I ended up still having the stream running, and I thought, oh, this will be kind of funny. But then Amanda went, ugh, because she had so much to do. She wasn't done working. The stream was just the beginning of her night, believe it or not. And she then had to do SkyTour News. She had to do other things that were, SkyTour related. And so she didn't... I
still had it up by about noon Sunday. I was done earlier. I was done by 8 in the morning. But I needed to double check for errors and
Yes.
one too many scoops
But
but oh well.
She works very hard, guys, so I know you appreciate her, and that's fantastic. I do too. I don't think the SkyTour livestream would be the same if we didn't have Amanda doing all these things in the background, like taking your questions and helping me out.
For better or worse, it wouldn't be the same, that's for sure.
Yeah, well, you know. So you guys can go listen to Jimmy Church now on KGRA if you want. He's probably up there now.
Or you could see who may or may not be filling in for Heather Wade on Dark Matter Digital Radio.
Yeah, that's
starting in about an hour.
That's a pretty big
going on over there.
Yeah,
so.
yeah. I was on Heather Wade's show at one point. Seems very nice. And you know, it was hard.
I don't know her personally.
Oh, okay. Well, I just know her from working with her on the show and here and there, just a little bit. She seemed very nice. I don't know what's going on. I think that, you know, she's having trouble with the fact that Art's gone, and who isn't? Art Bell. He was the blowtorch of paranormal for decades. So it's kind of hard when you lose your figurehead, your icon.
I wouldn't be here. I wouldn't know you, any of these guys, Bill, no one.
If it wasn't for Art.
To come back a few years ago.
Yeah.
And,
yeah.
Devastating loss for everybody. Yeah.
Mm-hmm. Absolutely
anyway,
is.
Don't want to end on a sad note.
Oh, we're not on a sad note. Art's in a better place. You know, he's already started over in a parallel universe.
He has the answers he's been looking for so long.
That's right, and he's not going to come back and tell us. He's going to say, haha, screw you guys. I know where I'm going. I'm heading over to parallel universe 62B over there. You know. All right. Guys, thank you guys. I will talk to you again, and the next clear night we'll be out here again. So we'll talk to you later. Have a good night.